Okay, thank you very much. So most important things are said already. The topic I'll be talking of, and it's about a tool and also our experience, which we made essentially driven by the operations in our company, where we run a lot of different storage systems, ranging from highest end enterprise applications down to supposedly simple Linux boxes running NFS or iSCSI. And well, maybe some of you share the experience we made in some places. I would like to start with a couple of examples. First thing is you run some kind of benchmark on your storage system, like Bonnie++, IOZone, or whatever is your preference, and it shows you get a throughput like 150 megabytes per second. Okay, so you are fine probably. Afterwards, you monitor what your real application is putting through, and it maxes out at somewhere like 50 megabytes. That's only a third. So what did your benchmark tell you? Example 2. You get a vendor of some systems around, and they say, okay, our super high-end storage system delivers 40,000 IOPS no matter what. After that, you notice that in operations it's like 10% of that maximum, never more. Although your applications would like to have a bit more than that. Or third examples, you get a new storage system from any kind of vendor, and it performs excellent. You are really happy with that. Over time it fills with data, and the fuller it gets, the more your performance drops, sometimes dramatically. And you start to think, what should I do in terms of benchmarking beforehand, so I can you can be sure that I get a system that's
please become louder toward the micro, please.
Closer? Better? Okay. So you ask, how can your storage system be benchmarked before you run into problems with, while running operations? We developed a solution in 1&1 where we tried to put a real application type of load onto the storage system. There's a lot of applications which offer application benchmarks, but that's what we developed is a bit more generic. So take a Linux system, for example, and the idea is to capture just the I/O on the block layer of the Linux kernel. Fortunately, in the Linux kernel, there is an interface for that, which is called blkreplay, block trace, and a tool set for recording data that goes over the block layer interface. So that tool records all the requests with the request timing, precise kernel timing, the length of the request, the type of the request, if it's read or write. It records the exact sector number it starts. So you've got everything in place to recreate that particular load up, that particular sequence of requests. And that's what my colleague, Dr. Thomas Schobel-Teuer, our kernel developer, just did. He developed that tool, blkreplay, block replay, which does this kind of replaying loads. One short note, the block trace interface is specific for Linux, but there's similar and compatible, sort of compatible interfaces also available for Windows or Solaris. So pick your favorite operating system and see where you can get the requests. Simple shell script should transcode that format to whatever block replay can read. Of course, there's a web page for lots of more information, the source code, full documentation, and even a lot of data sets we recorded at 1&1 in our data center. And best of all is everything, including the data sets, has been published using GPL or free documentation license. So you're really free to use that stuff and contribute if you like, or ask questions to us. And I think as a company that's using lots of Linux, that's the least we can get back to the community. So how does block replay actually work? Essentially, that picture is sort of as simple as it is in practice. You put whatever block trace got you into the standard input of the main process. There's up to 1,000 worker nodes which keep queues of the requests so that they can make sure that all the requests are fired at the precise exact timing as you like that. There's a bit of housekeeping here, and the results are being written out in standard out. So you can pipe data through that or use files for that, whatever you like. The result files are then processed by any tool you like. We deliver a set of scripts that are using GNU plot, and you get a bunch of nice graphs out of that. So let me show you an example. This is a storage appliance which we had in our test lab. And first I explain you how to read that kind of graph. This is just a duration of our test sequence. On the y-axis you see the throughput in I/O operations per second. The green line, or green pattern, is what we originally recorded. The yellow is what the tested storage system made out of that. We intentionally put a huge peak at the beginning of that test so we can see how the system would behave in overload situations and how it would recover. And what you see is that we get out something like 10,000 IOPS, which is, well, acceptable for the particular kind of storage system. Let's compare that to a Linux box with a couple of disks, which is about less than half the price of the commercial storage solution. This is has been a Linux box, essentially plain Debian Linux and an iSCSI target on top of that. So what do we get out? It's the same pattern, only the timing is a little bit different here, or the time scale is different. And you'll see the Linux box also delivers about 1,000 IOPS. So this is good news for open source and commodity hardware. But now something interesting on the next slide. Back to our storage appliance, which I showed you. This is just a second run with this, actually the exact same storage appliance which I showed you 2 slides before. But this time we filled it up with data. Remember, it's block layer, so no metadata stuff, no file system, nothing, as just a block layer. And I can assure you that the Linux system doesn't care if the disks have been written full or not. But evidently, this appliance does. What we get out is less than 5,000 IOPS. That's less than half than we get out of the empty system. And this is an effect we observe on many storage systems which are commercially available. And I show you why we think that might happen. So for us, it's the most likely explanation. So these commercial things are essentially black boxes. There's most of the time, and actually it's the SSD inside, and they implement some kind of storage virtualization. What does that actually mean in terms of physical effects? It actually translates the logical block addresses to the physical sectors on the disks. And evidently, it does some kind of reordering. And what happens is that usually benchmarks, including blkreplay usually, just touch a tiny amount of the disk space. So that's a small working set that's being handled by probably any kind of benchmark. So what these storage appliances do is, if that upper band would be the logical address space, and your benchmark touches a number of sectors randomly spread about the address space, the appliance would start reordering these in terms of physical location and put these just in the first couple of sectors of their physical disk space. So accessing that data is significantly faster than addressing the entire physical space. So that's one of the explanations that lead to that slowdown, depending if you pre-filled the entire physical address space or not. As a side remark, I may also say that commercial systems have been shown using block trace and block replay to consist evidently of a huge number of different software layers that are doing storage virtualization, that do thin provisioning, that do tiering and all that stuff. And what we learned is that every single layer of complexity in the first place costs performance. And for some working sets, for some behaviors, for some use cases, some of these layers can give you an improvement. But many of, especially the use cases we have in our company, don't gain on these layers of complexity. So these layers of complexity in a commercial box just cost performance. And this is essentially the reason why for some applications, the Linux box with nothing on top of that is the most efficient system. So let me conclude with about 1.5 minutes left on the kitchen timer.
5 minutes.
Your kitchen timer shows 2 minutes left, or 1.5 or something.
It's to have space for questions.
But that leaves a bit of space for questions, and probably one or two of you guys have some. Okay, so what have you learned? Synthetic benchmarks like IOZone, Bonnie, or whatever you use are not very predictive. They, of course, for some dimensions they have a predictiveness, but that's the reason why they exist. But compared to your real world use case, they are not very predictive. And the crucial factor that we identified for benchmarking is the structure of your workload you're running actually on your productive systems. What we can do with block replay is to recreate precisely these loads, which we recorded in real life operations. So there's sort of nothing synthetic on that. And the results of replaying that on a number of test systems gives us a detailed comparison of the behavior, like graceful degradation and graceful recovery or something, some other stuff. What I can also tell you at that point is that we have a tool set which is also able to modify your real life workloads into some kind of partly synthetic workloads where you have constant request rates or rising request rates. So you can play with your loads recorded in real life. So okay, the experience we made is clearly identified. So perfect timing. Again, if that sounds interesting to you, don't hesitate to visit our website or contact me or the author of that awesome toolkit as you like. And now that opens the opportunity to ask questions. Please?
Thanks. Did you run the same test with the filled block device on Linux?
Yes, actually we did. I didn't bring the graphs because they look right exactly by pixel the same. But we actually ran it and make sure that this is true. But by the way, on Linux you also have ways of introducing that kind of storage virtualization, like using LVM or whatever, like Ceph and a block layer on top of that. That's a huge opportunity, a huge amount of software that can do that, and we observe this kind of same effects.
So am I right in assuming that the behavior that you can show here don't really depend on the actual data that you read on the disk or write on the disk? So it is enough to have the metadata and the access pattern, but you do not need to include the actual data into the dumps?
That's right.
Okay, so the dumps do not get like 30 terabytes big so that you can have a small set of
No.
metadata and can still recreate a workload of 30 terabyte or so.
That's right. That's right.
Okay.
That's exactly right. We have only the metadata of the requests and not the content of the blocks. But beware. In the meantime, we have SSDs on the market that are compressing the data. So it's important to have a look at what kind of hardware you have on the bottom of that. If you have a compressing SSD somewhere in the system, you should think about preceding the data volume with some kind of random data, or where you know the compressibility. Zero blocks are very well compressible, and compressing SSDs handle that very well. We've measured that.
Yeah, that was my my follow-up question. Whether like in blkreplay you just pretend you read some random data instead of just all zero blocks.
Yes. So
Okay,
nothing prevents you of filling also real data on the disk beforehand, or do whatever you feel fit for your type of analysis. But on dumb disks, just reading zero blocks and writing zero blocks is okay. By the way, in terms of writing, we when we have a writing access to the blocks, we actually put a sequence number in there, so we can do verifications for afterwards to see if the sequence has been correctly replayed. There's test tools for that too.
Thank you for the talk.